What's poppin', dogs? Mr. Allen here, graphing a rational function in this video, and of course, answering all the wonderful questions we could possibly ask you on a test or a quiz. So first things first, we always check to see if it's factorable. I don't have to factor anything in this one, so woo, perfect. Domain restrictions, let's figure that out. Domain comes from your denominator. What would make my denominator 0? Well, if I plug -3 in here, -3 plus 3 is 0, 0 squared is 0, I can't divide by 0, that would make it undefined. It's a domain restriction. X cannot equal -3. Now, that's how I like to write it, but there are some bougie mathematicians out there that may want you to write it like this, where they'll say, okay, fancy set builder notation, teacher brackets, X such that X cannot equal, X equals all real numbers, and that X cannot equal -3. Close the fancy teacher brackets, all right? Settle down, people. It's a little too bougie for me. I'm more of this kind of guy right here, a little street math. Just tell you what you need to know. It's implied that it's all real numbers, okay? You can also write it in interval notation if you'd like. Okay, no hate here. I just think it's less efficient on this way, but this would work too. So if your teacher wants you to write it in that way, that works as well. Either one of those. This is how I prefer to write it in my classes, and this is my video. So I'm going to write it that way. But there you go. Just in case you needed to know, man. I got your back. All right, now, vertical asymptote. I'm going to save range for later on. Vertical asymptote for this one. Now, let's see here. Nothing canceled out, so there's no holes. Whatever's left, vertical asymptote. X equals -3. Beautiful. Okay, next one. Horizontal asymptote. Well, my degree of my numerator is smaller than the degree in the denominator. Therefore, my denominator will overpower it. Taking a number divided by an infinitely larger number than itself will approach 0. So, y equals 0. There are a few little tricks to that one. It's just that if the numerator is smaller than the denominator's degree, it's y equals 0. If they're equal, then you do the coefficients. If it's larger over small, then it's an oblique or slant asymptote. But I'll go over all those different scenarios in another video, okay? X-intercept. Let's see. How would I get an x-intercept? Well, that'd be when my function equals 0, meaning my y value would need to be 0. How can my y value be 0? Well, it definitely can't divide by 0. It'd be undefined. But if I got the 0 in the numerator, anything divided by, 0 divided by anything else besides 0 would give me 0. If -4 went in there, I'd have 0 divided by 1. Yay, it's 0. Cool. Numerator, x-intercept. Dope. Y-intercept. If I plug 0 in, what do I get? Well, I'd have 4 over 9. If I plug 0 in, right? 3 squared is 9. So I'd have 0, comma, 4 over 9. So the cool thing with like y-intercept is it's the same every single time, right? I always just plug in 0 for x and evaluate. The same goes with x-intercepts, but some of them are a little easier to find than others, right? So it's a lot of work to find x-intercepts. But still, 0 for y, 0 for x. That's how you get each of the intercepts there. All right, we'll do end behavior, vertical asymptote behavior, and range once we have the graph, okay? But let's plot some of these things. I'll use the pink, I guess, still. Vertical asymptote, x equals 3. -3, excuse me. All right, 1, 2, 2, 2, 2, 2. And I like to put a label on that thing to say, hey, it's x equals -3. Probably not necessary. Your teacher might not make you do that, but I often label my graphs just to be all fancy and bougie. X-intercept, -4, 0. Y-intercept, 0, 4, 9. It's right around a half, right? Anytime they're scaled out right here, you don't have to necessarily label it. Like a lot of times in polynomials, we leave it unscaled, and then we label our y-intercept. If it's scaled out, as long as I'm between 0 and 1, we're good to go there, all right? And then horizontal asymptote. Well, this is an interesting development, isn't it? I have a point on my horizontal asymptote. Crazy. How is that possible? I thought you can't touch or cross asymptotes. You can. You can cross or touch whatever a horizontal asymptote, but you will just always come back to it, okay? Horizontal asymptotes dictate the end behavior. It tells me what I'm heading to on the far positive and negative ends of the graph. Vertical asymptotes, never going to cross them, never going to touch them, or anything like that. You're just going to infinitely approach them, okay? But Horizontal, you can cross, okay? That's what I wanted to highlight here in this video, is that it is possible. All right, so then what the heck is happening here? I think it's very clear that my graph is going to be right here. For this section, but it's not very clear as to what's happening over here, okay? Now, there are a few ways to figure this out. One of them, and I would say stick to one method. It's up to you. I'm going to show you both. You can choose the one that works best for you. It's America. All right. X plus 3 squared. The asymptote, the vertical asymptote, the factor that we got it from, has a multiplicity of 2. Remember in polynomials, it would bounce if the factor was squared. It has a special little thing going on. Same kind of sort of idea here, except for with asymptotes, that means that it's going to get the graph approaching on the same way on either side of it. And this guy's just going to come back. Okay? So, because this asymptote factor was squared, the graph is going to approach it the same on both sides. Now, if it was not squared, they'd be going on different ways. Okay? But I know it can be kind of hard to memorize those particular rules. So anytime I don't remember a particular rule or I'm not sure exactly what's going to happen, I just plug in points, okay? I could plug something in that's really, really close to -3, right? This obviously -4 isn't going to do me any good because it's just on it. It doesn't really tell me. But I'm going to plug, like, say, how about -3.1? That's really close. It's somewhere like right around here, right? I'm going to plug that value in. And if it's a positive value, I know this graph is going up. If it's a negative value, I know this graph is going down. I don't even care what the value is, just if it's positive or negative. Well, I plug in -3.1. -3.1 plus 4 is a positive number. It's positive 0.9. But I don't care what the number is. I just care if it's positive or negative. And if I plug something in here, well, it's squared. It's always going to be positive. No matter what I plug in for x here, it's going to be a positive number, other than -3, obviously. So I have a positive divided by a positive. That's going to be a positive result. Hence, it's going up. Cool? Yay. Awesome. Same goes over here. If I plugged in -2.9 on the other side, right, the other number right here, plug that in, I get a positive over a positive. It's positive. They're both going up. So you can do little test values that are really close to it. I usually just go like a 10th place off, a 10th off of that asymptote, and test it and just see if it's positive or if it's negative. Right? I'm not worried about the actual number, just if it's positive or negative. That's also sometimes stuff for people to grasp of, like, I don't care what the number is. What? Really? Doesn't matter what the number is? Just if it's positive or negative? Yes. Okay. Tough thing to understand at times, but definitely something to figure out. I don't know what I'm saying there, right? Choose your hard, basically, right? Either remember if it's squared, you're approaching the same sides, or remember your test values. One or the other totally works, okay? All right, so the last things here. I'm actually not going to do range for this one. It has it, but we'd have to find this point right here. Let's just say this is like A comma B. Let's just say that's the ordered pair. There's some number right there, right? I could use my calculator, okay, and find the minimum there. We probably wouldn't ask you to do that on the calculator, or we'd be doing this as a non-calculator. But if this were the case, then I know that it's always going to be bigger than B right here. So we could say Y is greater than B, or you could say from B to positive infinity, that's going to be my range. Everything above this right here, this would be, greater than or equal to. I'd be including it. Boom. All right. So not something that we probably ask here in this particular problem, is we just wouldn't have range on there due to the necessity of having a calculator, right? All right, cool. Last little bit here, end behavior and vertical asymptote behavior. So let's do the end behavior now. What are we approaching on the far sides of the graph? We are approaching 0 on both sides. So as x approaches negative infinity, g of x, it's a beautiful g, is approaching 0, and as x approaches positive infinity, g of x is approaching 0. This will always match my horizontal asymptote. End behavior always matches the horizontal asymptote. Dope. And lastly, but not leastly, let's talk about our vertical asymptote behavior. As x approaches, it's -3 here. On the left-hand side, put a little negative there for from the left. G of x, we're going up, positive infinity. And as x approaches -3 from the right. G of x is approaching positive infinity. There we go, guys. We got it all. Everything done. That's dope and fantastic and wonderful. Thank you for watching, guys. I know rationals, it's kind of a beast, right? It's a beast of a topic here. A lot going on with rational functions. You could do an entire semester of just rational functions, I feel like, because there's so much that could possibly get mathed up here in these situations. But thank you guys for watching. Hopefully you liked it. If you liked it, like it, subscribe, and have a dope day.